Okay, so these are going to be some examples from chapter 26, our last chapter. We're going to just go through and do some practice with the transition metals, the coordination compounds. Okay. This chapter starts off with like a review of some of the material from the earlier chapters, and it's important review. So if any of this is unfamiliar, you really have to go back and take a look at some of that stuff we did around chapter 8 and chapter 9, where we discussed electrons and electron behavior. From writing electron configurations up to, how electrons are interacting in the orbitals. Okay. We're starting here by writing out the ground state electron configurations for neutral atoms as a reminder. And then we're going to move on to questions where we have to find the electron configurations for cations. Okay, so it's important first to know how to write the electron configurations of your neutral ions. Now, I think it's a good idea to kind of use your periodic table as a guide for this. All right, so I'm going to share my desktop real quick. And we are going to look and see how we can find the electron configuration, the electron configuration of zirconium using just using the periodic table, okay? Sorry, I'm not very tech savvy, so it takes me a second to do what I want to do. All right, move this here. Okay, so now I'm going to share. So now you guys can see my periodic table, hopefully. I'll laugh if that's not true. And we're going to actually use my little spotlight. I'm going to show you how I write out the electron configurations using my periodic table. We're going to start with the zirconium electron configuration. Okay, so the first thing I'm going to do is I'm going to find zirconium on the periodic table. Okay, it's over here, it's number 40. All right, and I would like to remind everybody about the different blocks of the periodic table now. The first two columns are called our S block. Okay, our last 6 columns are the P block. And this inner rectangle here is the D block. Okay, and then these 2 rows over here, which are expanded below, this is our F block. All right, and that's going to be describing the types of valence electrons that these things are going to have. All right, now, if we're going to figure out the corresponding energy level for each of these letters, which represent sublevels, we can look to the rows, the row number for each of the periods to find that principal energy level. So row 1 is going to represent our 1s group. Row 2 will be 2s, 3s, 4s, 5s, 6s, 7s. Okay, and the N value for your S sublevel will be the same as for your P sublevel. So if you have like 2S, when you come over here, this little row here of 6 elements will be your 2P elements. These are your 3S elements, and then these will be your 3P elements. Just know that this helium, even though it's over here, you can imagine that it sits right here next to hydrogen. So hydrogen would be 1s1 and helium would be 1s2. Because those are the only 2 elements that only have period 1 electrons or energy level 1 electrons only. Once we move on to the D block of elements, which is where we spend most of the time in this chapter, we have to remember that the D sublevel corresponds to 1 principal energy level below the S level that precedes it. Okay, so for this first row of our D electrons here, we are going to be in the 4s sublevel when we're in, when we have our first our potassium and our calcium here. But when our D electrons start, scandium starts with 3d1. Okay, so this is 4s1, this is 4s2, this is 3d1. Then 3d2, 3, 4, all the way up to 3d10. When you move over to gallium, you jump back up to n equals 4. So this is going to be 4p1, 4p2, 4p3, up to 4p6. All right, and the same thing is going to happen here. This is 5s1, 5s2. Yttrium is 4d1, up to 4d10. And then it jumps back up to 5p. All right, so like I was saying with zirconium, the way that I would write my electron configuration for this is first I'm going to find zirconium, and then I'm going to go back to the noble gas that comes right before it. Okay, so that's going to be noble gas 36 krypton. Okay, and I'm going to put krypton in brackets. Okay, and then I can use my periodic table to fill in the rest of the electron configuration, because I know that this right here, this is my 5s sublevel. This is 5s1, this is 5s2. So I know that both of those 5s electrons are going to be used. Zirconium is only 2 into our 4d block. So I'm going to have an electron configuration that ends with 4d2. If I was ending with molybdenum, it would be 4, well, let's not use molybdenum because that's a little bit an exception area. If I was ending with ruthenium, it would be 4d1, 2, 3, 4, 5, 6. Okay, palladium would be 4d8. All right, so you can count where we are on the periodic table, and there are some exceptions that we did cover back in chapter 8, having to do with half full sublevels and full sublevels, right? So like your chromium exception and your copper exception, those exceptions expand to more elements, but for the majority of them, you can just count where they are on the periodic table to figure out how many d electrons they're going to have. Okay, so our electron configuration for zirconium is Kr 5s2 4d2, and that's the neutral configuration. Okay, hopefully that makes sense. The second example was for osmium. Okay, so again, I would find osmium on the periodic table. It's number 76. I would go to the noble gas that precedes it, which means comes before it. And that's going to be xenon. All right, and then I'm going to use my periodic table to count all the electrons that are used until I get to osmium. Okay, so osmium is in the 6th row, which means I'm going to start with the 6s2 electrons. Okay, and then I'm going to run into my lanthanide series. Okay, before I get to the rest of my D block, I'm going to run into that lanthanide series. Let me just pop up that share screen again to show you what I'm talking about. So I'm in my 6th row here, and this is 6s2, but before I can get into my D electrons, I have to deal with this lanthanide series. Now, because I'm looking specifically at osmium, I know that I'm going to be filling all of the electrons in my F block here. Okay, and your F block is going to be numerically 2 principal energy levels lower than your S block. So because this is 6s, my F block is going to be in principal energy level 4. And I'm going to use all the electrons in principal energy level 4. So it's going to be 4f14. After I'm done with my F block, I'm going to jump back up into the D block. And it's going to be 5d, because it's going to be 1 less than my S sublevel value. Okay, and then we can physically count over to osmium. It's 1, 2, 3, 4, 5, 6 electrons in. So it's going to be 5d6. All right, so that's how we're going to write neutral electron configurations. And we spent the time looking at this because we have to be able to write correct neutral configurations before we can write ion configurations. And the ion configurations are incredibly important to the stuff that we do in this chapter. Okay. So the next example is asking us to look at ions instead. Let me pull it up here. And we're going to look at CO3 plus and NB2 plus. All right. So if you want, this would be a good time to just pause real quick and try them on your own and see, you know, give it a shot, and then you can compare it to what I come up with. All right, but we're going to be doing CO3 plus first. Okay, so again, when I do this, I start out by writing the neutral configuration first, and cobalt is element 27. So that's going to be AR, and then it's going to be 4s2, and then 1, 2, 3, 4, 5, 6, 7, 3d7. Right, 1, 2, 3, 4, 5, 6, 7. Okay. Now, if I want to turn this into cobalt 3 plus, that means that I have to remove 3 electrons. Okay, but you cannot remove just any electrons. Specifically here, we have to start by removing electrons from the highest N level first. Okay, so from the highest principal energy level. Okay, so basically because 4 is bigger than 3, we're going to remove the electrons from the 4th level first. So both of these electrons get removed. Okay, now that goes down to 0. Now I still need to remove 1 more electron because I need to remove 3 of them. So I'm going to take 1 away from the 3D. So my electron configuration for the cobalt 3 plus ion ends up being AR. And then you don't have to write 4s0, you can just skip that. And you can write 3d6. I mean, if you write 4s0, that's not a big deal. But this is what we end up with. All right. Our next one is going to be NB2 plus. Okay, so again, we're going to start by finding it on the periodic table and then writing out the ground state structure. It's atomic number 41. So our noble gas that precedes it is going to be krypton. And we're going to be in the 5th principal energy level for our S's. So it'll be 5s2, 4d3. Okay, and again, to turn this into an ion now, I'm going to focus on the highest principal energy level first, not what I wrote last, what the highest number is. And this is going to be a +2, so I need to remove 2 electrons, and these will be the 2 electrons that I remove. Okay. So my electron configuration for NB2 plus is going to be Kr 4d3. Okay, so it changes, making sure that you're pulling electrons from the right place changes the value that you get over here, changes what your configuration of your ion is. And that's going to be important later when you're deciding how many electrons are in your octahedral diagrams, right? When you're looking at the magnetism. So it's very important to be able to figure out the correct electron configurations for these cations. All right, but a little bit of practice, it's not that bad. All right, our next question has to do with naming. Okay. So we're gonna have a little discussion before we can talk about the naming. Because I'm gonna blow through some stuff here and I don't want you to be like, you know, what are you talking about? When we're talking about coordination compounds, we're talking about a compound, which is neutral, that's made up of at least one complex cation, maybe two, but at least one. Okay. So you can write down these formulas real quick. When I want to go through a little bit of background though. All right. When you are looking to name your coordination compounds, you have to understand that whatever is written first is going to be your cation, and whatever is written second is going to be your anion. Sometimes the cation is your complex ion. Sometimes the anion is your complex ion. Okay? And whether your complex ion is your cation or anion changes how you name it. So one of the examples that we have here is CrH2O 5Cl2. Okay. The cation always comes first in a chemical formula. That means that this is a complex cation. You can tell it is a complex ion because it's in brackets. That's going to be your big hint there. And your counter ion, well, your counter ions are anions. And you know that they're anions because they come last in the chemical formula. Okay, if you think all the way back to the beginning chapters when we were first talking about chemical formulas, you should be comfortable with that idea by now that your positive charges are listed first in your chemical formula and your negative charges come after. Okay. Now, in one of the next examples that we'll look at, you might see something like this. K3 Fe CN6. Okay. What is still true about this compound is that the thing that's listed first is your cation, and the thing that's listed second is your anion. Okay, but this time the big guy in parentheses here is an anion. So we're going to call that a complex anion. And your counter ions are cations in this one. All right, so when we're talking about the different rules for naming complex cations versus complex anions, that has to do with whether your bracketed ion comes at the beginning of the chemical formula or at the end. Okay. What's also true is that within your brackets, even if you have a complex anion, so overall here, an anion means that this is going to have a negative charge overall. Even though this ion has a negative charge overall, the charge on your metals are always going to be a positive charge. Okay, like if it's going to have a charge, it's going to be a positive one. Your metals aren't going to have a negative charge. Okay, so even if the metal is part of a complex anion, the metal itself is still going to have a positive charge. All right. So that being said, let's look at this. All right, so we're looking at this compound here. And your textbook goes through steps, and I think that they're good steps. for naming these. They tell you, first of all, to look at the ligands and to just name the ligands. Okay, so when you see H2O, which is water, the name of that particular ligand is going to be aqua, right? You have to know the proper name. You can't just write water in there. Okay, the name for the chloride ion is going to be chloro. Right? And you want to put these in alphabetical order. I would put them in alphabetical order before you look at any of the subscripts and you try to like put prefixes on there, because the prefixes are not included in the alphabetizing. So a lot of times it's easier before you even look at this 5 just to make sure that these two things are in alphabetical order. And they are right now because A comes before C. Now that that's true, now that you've got that all set and you're like, yeah, that's correct. Now you can look at that 5 and you can put a prefix in front of the water. Okay, so now you can call that penta aqua. And I'll fix this up a little bit later. This is just how I go through and make my notes when I'm doing this. Okay. The next thing that we have to do is we have to figure out what the charge or the oxidation state of the metal is that's in the complex ion. Okay, and we have to use all of the information that's in that formula to help us out there. So what you're going to do is you're going to go through and you're going to assign charges to everything in this coordination compound except the central metal. And you're going to use all of this information to figure out what the charge is on this. Okay, so for example, you know that every chloride ion has a -1 charge, right? And altogether we have 1, 2, 3 chloride ions here. So then the chlorides are giving us a total of -3. Water has no charge, got a charge of 0. So the other thing that we have to be aware of, and it's worth mentioning because I did have a question about this, when we're looking at a coordination compound, meaning that there's a cation and an anion present, all compounds are neutral. Okay, so they have no charge on them. That means that when we add up the charges of everything in this compound, it should add to 0. So that means that my chromium ion plus the water plus the 3 chloride ions needs to equal 0. And what that means is that my chromium ion has a charge of +3 or an oxidation state of +3. Okay, so using that method, we just figured out what the charge on the chromium is, and we need this charge as part of the name because you have to name the charge along with the metal for these. Okay, so this is going to be chromium 3. And notice that because my complex ion here is a complex cation, I'm not going to change the suffix of the ending of the metal. I'm just going to call it chromium and then a 3 in Roman numerals. Okay, so now we're going to put this together and we're going to form the name. Like all compounds, you're going to name the cation first, the anion second. And if you're ever confused about that, bring it back to something that you know. It'll be just like if you were naming NaCl. You name the cation first and the anion second. It's sodium chloride, right? It's not like chlorosodium. No, it's sodium chloride. We're doing the same thing here. It's just that the cation has a little bit more of a complicated name. Okay, so to name this cation, we're going to name the ligands first, and we're going to name the metal last. Okay, so we already have our ligands in alphabetical order. We're going to put A first, C second. So it'll be penta aqua. There's only one chlorine, so I can just write chloro. This is chromium 3. And now I've named the cation. And now I'm just going to finish it up by naming the anion. And you don't have to do anything special to name the anion. It's the same, again, as if you were naming like NaCl. So if you have 2 chlorines attached back here, that's just going to be chloride. Penta aqua chloro chromium 3 chloride. All right. Okay, let's look at the next example. It's going to be another cation, just so we can get another bit of practice with that. Okay. So again, you can maybe you can start by you can either start by listing out the ligands like we did before, or you can find the charge first, whatever makes you happy. I like this naming the ligands first though. So we can pull out that CO. We know that the name for that is going to be carbonyl. We know that the name for the ammonia is going to be amine with 2 M's. Okay, so when we're putting these in alphabetical order, we know that the amine is going to have to go before the carbonyl, right? So we can put like a little arrow there. Now to figure out what the charge is on our metal, we're going to look at the charges on everything else. Okay, and we know that everything has to end up with a neutral, right? It's neutral. It has to end up with a 0 charge overall. We know that the sulfate ion has a -2 charge. Okay, and then you have to ask yourself, do any of my ligands have a charge? And in this case, they don't. Both of these ligands have a 0 charge. They're neutral. So we could put like little zeros here. Okay, so if my sulfate has a -2 charge, then my manganese has a +2 charge. All right, so that's going to be manganese 2. So now I can name this. I have 5 amines, so that's going to be pentaamine. And then I'm going to name the carbonyl. And then I'm going to name my metal, including the charge. And I'll follow it with my, with my anion. Okay. So now we can take a look at the complex anion naming. So you can see how it's a little bit different. It's very small change. I mean, you're just going to be altering the very end of your metals for the complex anions. That's it though. The rest of this process is going to end up being the same. Okay, so we have K3 brackets Fe CN6. And then we're going to have Na2 PT Cl4. All right. So right off the bat, again, we can tell that this is a complex anion because cations are first, anions are second. And when we have brackets around it like that, we know it's going to be a complex anion. All right, so we can start by naming our ligand. We have the cyanide ion in there. The name for that is going to be cyano. All right, and there's 6 of them. So there's only one type of ligand, so we don't have to worry about alphabetizing here. We do know that this is going to be hexacyano when we're ready to do that. But now we have to figure out what the charge is on our central metal in the complex ion. And we're going to do it the same way. Okay, I know that we're in an anion here, and sometimes that freaks people out a little bit, but you know, you're going to go through the same process. We have 3 sodiums. If you look on your periodic table, you see that sodium is a group, potassium, we have 3 potassiums. Potassium is a group 1 metal. It has a positive 1 charge. Okay, so we're going to do 3 times positive 1 means that you have a positive 3 charge from the potassium. Okay, you have 6 cyanides. Each cyanide, if you need a little reminder, cyanide is Cn-1. So each cyanide has a negative 1 charge. So we're going to have 6 times negative 1, which will be negative 6 from the Cn-. Okay, so that leaves me with a negative 3 deficit right now. That means that the charge on my iron is going to have to be positive 3 in order to make my compound neutral. All right. Now the names for some of the metals change when we are working with complex anions instead of cations, which we talked about. Iron's name changes more than most names, because instead of like just adding an ATE ending to iron, we have to change the name of it to ferrate. Okay, so we're kind of like doing a throwback to the older naming system with that. So we're going to call this the ferrate 3 ion. All right, but now we know everything, so we can name this, and we're going to start the naming with the cation, like we always do. We're always going to name our cation first, and this is a simple cation, and just like any other ionic compound, even though there's 3 potassiums, we're just going to name it with the name of the metal, right? Because when we have ionic compounds, you know, if you have K2SO4, for example, this is just going to be potassium sulfate. You don't have to tell us how many potassiums are there. We know how many potassiums are there based on the charges of everything. So we'll start by naming the metal, like the metal cation there, so it's potassium, and then we can name our complex anion. Okay, so that'll be hexacyano, and then ferrate 3. Okay, and that's it. It's named. All right. Let's try this one. So we can go through and do the same thing. We only have one type of ligand again here. We just have the Cl, which is chloro. All right. As far as charges go, we have 4 chlorines, which is going to be -4 total. We have 2 sodiums, which will be a +2 total. That means that our platinum is going to be a +2. All right. While we're sitting here and we have both of these examples up, let's just take a minute to look at the coordination numbers of these. Coordination numbers are going to be the number of attachments the central metal has. Okay, and the different ligands potentially have different numbers of lone pairs of electrons that they're able to like contribute to the central metal. So you have to know whether each ligand is monodentate, meaning it only has 1 lone pair to contribute, or bidentate, meaning it has 2 lone pairs to contribute, up to hexadentate. something like EDTA, which has 6 lone pairs to contribute, right? Once you know how many lone pairs the ligand has to contribute to the central metal, then you're able to look at the formula and figure out the coordination number of that central metal. So for our first compound here, we have 6 cyanide ions attached to that central metal. Cyanide is a monodentate ligand, and that means that the coordination number of that iron is going to be 6. Okay. Chlorine is also a monodentate ligand. So the coordination number of the platinum here is going to be 4 because I have 4 chlorines attached to it. All right. I just wanted to point that out. I'll do another coordination number count in the next question too, because they don't actually have a question about finding coordination numbers in this list that I'm going to be going through. All right, but back on track. We know what the charge is of our central metal. We know what the ligand is. Now we can name this. Okay, so we're going to start by naming the metal cation here, the sodium. Then we're going to name our ligand. There's 4 chlorines, so it'll be tetrachloro. And then we'll follow it by the name of the metal. So this one is going to be platinate. This is where we change that ending, and we'll include the charge. All right. I think we'll name these ions too. I'll do it a little bit quicker for the next question. But before we look at the isomers here, I think that we're going to just name these because at least we have some different ligands that they're introducing here that weren't introduced in the last one. So these are just complex ions, and you can tell that something's a complex ion versus a coordination compound because it still has a charge on it. Okay. So you could name the complex ions or you could name the full coordination compounds. You just, at the end you'd say ion if it's an ion. But let's look through and let's just name these real quick. And then we can look at whether, what types of isomers they form. All right. And I'll try to help you see the trend there. So we have CO, En2, Cl2 plus. All right. So over here, we have a complex cation. We know that because it has a positive 1 charge. It's got 2 ligands, 2 types of ligands. It's got ethylene diamine and chloro. Okay, so we're going to want to put that out front. I wanted to name this one because the other examples don't include the other types of prefixes that you need to use when you run into this specific situation where you have the name of one of your ligands, and within the name itself, there's a prefix. Okay, it only happens for your list of ligands with ethylene diamine and then the ethylene diamine tetraacetate, the EDTA. The rest of them are going to be normal. But for your ethylene diamine and your EDTA, there is at least one prefix. In the EDTA, there's more. That's within the name of the ligand itself. So they're going to need a different prefix to put out front that indicates that there's more than one of these full ligands. All right. But we'll get to that when we're doing the number part. So let's find the the charge on the cobalt here. We know that there's 2 chlorines, so it's going to have a -2 charge. The ethylene diamine is neutral, so that'll have a 0 charge. And we have to end up with a +1 charge. Okay, so basically cobalt, the cobalt -2 has to equal +1, right? Because that's a contribution from the chlorine, and that's the overall charge on the ion here. I like to set it up like little math problems. So the cobalt ion is going to have a charge of +3 here, right? And that should make sense, right? Because if you have +3 cobalt and you have -2 chlorine, you're going to have an overall charge of +1. So with all that information, we can name our complex ion. We're going to have 2 chlorines. So that's going to be dichloro. And then we're going to have 2 ethylene diamines. And the prefix, the specialized prefix, meaning 2, is bis. So you just have to put bis in front of ethylene diamine. Okay, and then we'll name our metal. And because it's a complex cation, we don't have to change the name of this metal. All right, so I just wanted to throw that in there because we didn't have any of these specialized namings in the examples that we went through. All right, so now let's look at the isomers of this guy. Okay, now I did my best with this to try to show, I did little molecule guys here that we can talk about, okay, to try to demonstrate the different types of isomers. I think sometimes it's a little bit easier to see when you have the structures in front of you like this. Okay, so you're going to have cis isomers and trans isomers here, right? Your textbook gives you generalized formulas that can like help you identify whether you have cis-trans isomerism or FAC-MER isomerism. Okay, so if you have a type of isomerism where you have, it's your central metal, that's what the M is going to represent. And then one of your ligands would take up 4 spaces and another ligand takes up 2 spaces. This type of orientation is one that can lead to cis-trans isomerism. Okay, and with this formula, we have 2 ethylene diamines and 2 chlorines, right? Your ethylene diamine is, this is a great question too for coordination number, man. Your ethylene diamine is bidentate. So it's going to have 2 places on the molecule where it can attach to the cobalt. Okay. Speaking of that, if we were going to find the coordination number of the cobalt in this ion, we would have to take into account that each ethylene diamine is going to attach at 2 points, right? It attaches at 2 points to our central metal. So each ethylene diamine contributes 2 to the coordination number. And there's 2 of them. And there's also 2 chlorines, which are monodentate, which are only going to have 1 attachment point. So the overall coordination number of an ion like this is going to be 6. Okay. Now, cis-trans isomerism has to do with the location of, I like to think of it personally as the location of these 2 things, of the 2. Okay. If the 2 things are next to each other or if they're across from each other. Okay, so this is an example of the trans isomer because the 2 chlorines in this case are across from one another. All right, I think it's easiest to recognize like which type of isomer is trans versus cis based on whichever you have fewer of. Okay. Once you are looking at the cis isomer, now your two chlorines are going to be right next to each other. Okay. So that's going to be a representation of your cis isomer. Hopefully that makes sense. The second example, what was it? Okay. Second example that they give us is Cr H2O 3 Cl3 plus. Okay. I'm going to name this again real quick because I think it's a very good idea to be practicing this. We have 3 chlorines. That's going to be a -3 charge. We have 3 waters. That's going to have a 0 charge. Chromium -3 has to equal +1. So our chromium is going to be +4 here. Okay. This is a complex cation again, we know because it has a positive charge up here. I'm going to have to put my aqua before my chloro because A is before C. And now I can name that triaqua, trichloro. Chromium 4 ion. Okay. We also know that this has a coordination number of 6. Because there's 3 chlorines and there's 3 waters. And chlorine and water are both monodentate ligands. All right. Now, the general formula here is different, okay? What we have here are 3 of each types of ligand. So the generalized formula is, if M is our central metal, is going to be that we have 1 ligand with 3 and another ligand with 3. Okay, this general formula is one that can result in Fak-Mer isomers. Okay, 3 and 3. Now, it might be, it's sometimes easier to understand what this type of isomer is if you really break down what the names of these things are. Okay, the Fak isomer stands for facial, I think. But what this means is that the ligands, like all 3 of one of these ligands, are going to take up one face of your octahedron. Okay. The mer stands for like meridian or meridional or something. And in this version of the isomer, 3 of your ligands are going to kind of, they make almost an arc around the middle. Okay. And that's where like the meridian term comes from. So I kind of, let's see, are they over here? I was trying to create these before I started this video so that we could look at them. Okay, so we're going to have, we have 2 types of isomers. This would be considered the Fak isomer, the facial isomer, because you have all 3. It doesn't matter whether you're calling these the chlorines or the waters, right? But all 3 of these ligands are grouped on one side and all 3 of the other ligands are grouped on the other side. So one face of your octahedral is just going to be I don't know, chlorines. The other face is going to be the waters. All right. So you're going to see the cluster of 3 each next to each other for the FAC isomer. For the meridional isomer, the arc that I'm talking about happens because you see you have, let me start, yeah, like this. See, this is like the middle of your, this is like your central plane here. And what do we have? We have an arc around the middle. Okay, so the three ligands are not grouped in a way that puts them on the same face. Instead, they're lined up so that they're crossing the middle of the structure. All right. You're going to notice that when you have your FAC isomer here, like no matter what way I'm holding this, I always end up with different ligands on the top and the bottom. Okay, it doesn't matter which way I put it, I'm always gonna have different ligands on the top and the bottom. And that's because all, they're grouped in a way that puts them all next to each other. In my meridian, I can orient this in a way, I mean, it's not every way, but I can spin it and orient it in a way so that I have 2 of the same ligands. Okay, I have the option of that here, or I don't have the option in the other one. Okay, but I do see that my ligands form this arc along the center. Okay, arc along the center. That's the meridian isomer. And then this is the FAC isomer. So that's going to be a face, right? They're all grouped together like that. This is going to be another face. They're grouped together like that. All right. I hope that visualizes it better. I have a lot of trouble seeing the isomers. So I do feel for people when they're trying to learn this. I'm definitely a person that when we were doing optical isomers in Gen Chem and in organic chemistry, I needed the model kit because I couldn't just see them. Like some people you can describe this to someone and they can see it and I can't see it. Like I have to be like holding it in my hands and looking at it. But that's all right, That's why you got to figure out what works for you, basically. We're going to look at that first isomer and we're going to decide whether it's optically active now. Okay. So we'll bring these ones back in here. I didn't have enough to make 2 of the trans isomers. So we'll talk about the cis isomers first. I'm hoping that you can kind of, yeah, then we'll do the trans one. All right, so they want us to look at the cis and trans isomers here and decide if they're optically active. Okay, something is going to be considered optically active if they do not have a superimposable mirror image. That's the wording of it. Okay, so we're going to talk about what that means. So this is a cis isomer. Remember, we have the 2 chlorines next to each other and then the 2 ethylene diamines next to each other. So to start with, when you're deciding whether something is optically active or not, you have to kind of imagine them like they're staring at each other in the mirror. Okay, so like everything's the same, they're looking at each other. And then you have to flatten out that mirror image. All right. Then you have to take that mirror image and you have to put it on top. Okay. When you put it on top, and I know this gets a little bit harder to see because, we're not in person or anything, and I don't have like a good 3D screen. But when you put it on top, if the orientation of all of your atoms is identical, then there's no optical activity. If there's any differences, though, then there is optical activity. Okay. Now, the idea that you can use your hands is often talked about here because, like, you could say that your hands are mirror images of one another, and then if you flatten your hands out and you put one hand on top of the other, like your pinky and your thumb, well, there you are over here, and that's not going to change, right? There's no way you can like rotate your hand within the same plane and make them the same. All right, that's what we're looking for here. So when we take our mirror image, we flatten it out, and then we try to put this flattened out image on top of the other one. There's differences, okay? The orientation of these is different because these two, just bang them together, these two things are going in different directions in space, okay? And even if I rotate it, okay, even if I rotate this molecule, I still have a different orientation. It's still not identical. No matter what way I rotate this in the same plane, I am never going to be able to make the cis isomer fit directly on top of its superimposed image and make it so that the both shapes are the same. Okay. When that happens, that causes optical activity. Okay. When you can't make the mirror image sit on top of each other perfectly, that's what causes optical activity. Now let's look what happens in the trans isomer. Okay, I just have to rearrange this real quick. Okay, I use a different color central atom just so we can keep track of them. All right, so they're looking at each other in the mirror. Okay, we flatten them out. And now I put one on top of the other. This is exactly the same. See, like there's no difference there. Everything's in the same plane. They're perfect. No optical activity here. This one is not optically active. All right, so those are the differences that you're looking for when you're trying to decide whether something is optically active. So hopefully that's a little more helpful than just the two-dimensional pictures in the textbook. All right, the next question is going to bring us back to some math. Okay, I included the color wheel in this question as a guide because I think that if you saw a question like this, something like a color wheel would probably be included for reference. So you could pull out the appropriate wavelengths from these. So the first question says that the complex ion for CuNH3 6 is blue in aqueous solution. We're going to estimate the crystal field splitting energy in kilojoules per mole for this ion, kilojoules per mole. Okay, so let's write that down, kilojoules per mole. Okay, now there's a few things that you have to be able to pull out of this question. First of all, they're saying that the solution itself is blue. If a solution is blue, that means it's absorbing its complementary color, right? So if a solution is showing blue, that means it's going to be absorbing orange. All right, so that's the first association we have to make here. We have to know that it's absorbing orange. And because we're estimating the crystal field splitting energy here, we can guess that the wavelength for like the middle ground over here would be somewhere like maybe 6. Let me just take oh, there it is. I'm just going to take an average. All right, 615. So we're going to say that the wavelength of average orange light, which is right in the middle here, will be like 615 nanometers. And that is all the information that we need to answer this question. Okay, we have a formula back from chapter 8 again that allows us to find the energy, right? In that chapter, we talked about finding the energy of a photon. In this case, we're going to kind of rename it. Okay, but it's the same idea. We're going to call it the energy of an ion. Okay, and the energy of an ion is going to be equal to Hc divided by wavelength. Okay, so you might have to remind yourself of what some of these values are. Now, luckily, they are on the constants list in the in your textbook. Okay, H is Planck's constant. That's going to be 6.626 times 10 to the negative 34 joules per second, joules times seconds. Okay, C is the speed of light in terms of meters per second. Okay, and your wavelength, because our speed of light is in terms of meters per second, our wavelength has to also be in terms of meters. So it might be a good idea to, before you plug it into your formula, if you have 615 nanometers, we know that there are 10 to the 9 nanometers in 1 meter. Okay, so now we can plug that value in and it will already be in terms of meters. All right. Now we can calculate the energy, the crystal field energy of one of these ions. All right, and we get 3.23 times 10 to the negative 19 joules. And that is going to be our crystal field splitting for one ion. And remember that little delta sign, that's what this chapter uses to note crystal field energy. Okay, that's the delta for one ion. We want a value in terms of kilojoules per mole. All right, so I have to do a couple of things here. I have to divide this by 1,000 so I can turn it into kilojoules. And I'm going to have to, kilojoules per mole. And I'm going to have to use Avogadro's number to get me in terms of moles instead of just one ion. Because right now I know that I have 3.23 times 10 to the negative 19 joules for every one ion. Okay, but that's not going to cut it for the value that I need to calculate. Okay, so instead I'm going to say, well, I know that there are 1,000 joules in 1 kilojoule, right? So that is going to allow me to divide by 1,000. And I know that in 1 mole, there are 6.022 times 10 to the 23 ions. Okay, so now I'm going to be left with kilojoules over moles, which is what I want. All right, so I end up with a crystal field splitting energy of 195 kilojoules per mole. Okay, so it's not that bad, just a couple steps. Let's look at the next one. Okay, the second example says that our complex ion is yellow. And again, we're going to be estimating the crystal field splitting energy in kilojoules per mole. So we see that if it's transmitting yellow light, that means it's going to be absorbing violet. Okay, so probably the average of our violet light over here is going to be around 415 nanometers. Let's write that down. Absorbs violet around 415 nanometers. Okay. We could take this nanometer value and we can put it into meters right away now that we know the process. We know that we're going to need this number in terms of meters. Okay, and now we can find the energy of an ion using Planck's constant. Times the speed of light divided by our wavelength in terms of meters. Okay, so we get 4.79 times 10 to the negative 19 joules per ion. Okay, now we're going to look at that in terms of kilojoules per mole. So how many kilojoules per mole equals 4.79 times 10 to the negative 19 joules per ion. 1,000 joules in 1 kilojoule. In 1 mole, I have 6.022 times 10 to the 23 ions. Okay, so I end up with 288 kilojoules per mole. And that is my crystal field splitting for this ion. Okay. Next question has us going back into these diagrams, okay? High and low spin octahedral complexes. So this is where we have to start using the ion configurations that I was talking to you about before. So we're going to be looking at CO F6 3-, and then FeCl6 3-. Both of these are complex anions, right? Just to be clear. And what we're looking for is unpaired electrons and whether the species is paramagnetic or diamagnetic, right? So you're going to start any process like this by figuring out how many electrons the central metal has, okay? So for cobalt, we know that the cobalt ion here is going to be CO3+, right? Because there are 6 fluorines. Each fluorine is a -1, which is a total of -6. So cobalt has to be a +3 so that they can add together to get -3. Okay, so now we're going to have we need to get the electron configuration for the CO3 plus. Okay, so we can look at our periodic table. Cobalt's over there, number 27. Neutral cobalt is going to be 4s2, 3d, 1, 2, 3, 4, 5, 6, 3d7. So I'm going to take off these 2 electrons from my 4s because it's the higher energy level. I'm going to take off one of those. So I'm going to be left with 6 3d electrons, right? That's going to be what's left over, 3d6. And that 6 in the superscript, that tells you how many electrons you have to work with. So we have 6 electrons. All right. Our octahedral complex is talking about the orientation of the 5d orbitals. Okay, remember that our d sublevel has 5 orbitals, and in an octahedral orientation, 3 of those orbitals are going to be on a lower level than the other 2. Okay. The distance between here, this is your delta value. That's your crystal field splitting energy, right? When your crystal field splitting energy is small, let's say if delta is small, your electrons are able to spread out because the energy difference between the 2 levels is negligible. And so your electrons can just kind of spread out and follow their ordering rules from your, that you've already learned about. And you end up with what are called high spin complexes. And they're called high spin complexes because say that you have 6 electrons here, right? So if your delta value is very small, then the 6 of those electrons are just they're gonna like spread all the way out as much as possible, right? But if your delta value is large, I don't know why I colored it in, I just wanted to. If delta is large, this leads to what are called low spin complexes. Okay, and that's because electrons, I told the one of the other groups this too, electrons behave a lot like people. And so if this delta value gets very big, when that 4th electron has to fill a spot, if the energy is too high, it's going to look up like this giant staircase it has to climb to get up here, and it's going to say, no, thank you, I'm not going to go up there. Instead, I'm going to go back to the beginning and just sit over here with this guy because I don't feel like making that climb. Okay, so 6 electrons in a low spin complex will try to stay on the bottom level with the low energy. So you see how I only end up with 1 unpaired electron here, right? That's why it's called low spin. When all my electrons were spread out, I had 4 electrons with no pairs. That's high spin. The more single electrons you have, the higher your spin is. The more paired electrons you have, the lower your spin is, because when you have 2 electrons together, their spins cancel each other out. Okay. Now you very reasonably might ask, well, how am I supposed to know if the delta value is big or small? And the answer goes back to this chart that you were given. It's in your textbook, and it's in your handouts that Professor Sheehan gave you. Okay. The type of ligand attached to your central metal. Okay, and remember, in this case, in the example we're doing now, the ligand is fluorine. The type of ligand depends whether you have a big delta value or a small delta value. So you see these ligands over here, they're called strong field ligands, and these have a large delta value. If your central metal is attached to a strong field ligand, then you're going to have a low spin complex because you're going to have such a large space between those energy levels, and that top level is going to be at a much higher energy than the lower one. If your central metal is attached to a weak field ligand, weak field ligands are going to have a small delta value, a small crystal splitting energy. And that means that the electrons will be able to spread out, because even though you have a low level and a higher level, they're still close enough together. It's like taking a step up a curb versus climbing up 3 flights of stairs, right? Like going up one step is not a big deal. And so electrons are able to like spread out in that manner then. Okay, so we have to look at the ligand that's attached, in this case fluorine. We have to find it on the list. Here it is. It says fluorine is typically a weak field ligand, so fluorine is going to have a small delta value. All right, knowing that, we can now distribute our electrons according to this rule up here. If delta is small, we're going to have a high spin complex. So our 6 electrons are going to spread out as much as possible. 1, 2, 3, 4, 5, 6. So we're going to have a high spin. Okay, we have a high spin complex with 4 unpaired electrons. When we have any unpaired electrons, this means that our species is going to be considered paramagnetic. All right. So let's look at FeCl6. So let's see, what can we erase some of this? Yeah, we'll just erase all of it and do it again. All right, so right off the bat, I'm going to want to figure out what my charge is over here. I have 6 chlorines. That's going to be a -6. I have a -3 charge overall. That means that iron is going to have to be a +3, right? Because +3 and -6 equals -3. So I have to find the electron configuration for the Fe3+ ion. Okay, go find iron. It's number 26. So neutral iron is going to be 4s2, 1, 2, 3, 4, 5, 6, 3d6. And I'm going to remove 3 electrons. So I'm going to remove these 2 and then 1 of these. Okay, so my Fe3+ is going to be, if we want to make it official, put the argon out front, Ar3d5. But what we're concerned with is that we have 5d electrons, because those are the electrons that we're going to distribute in our octahedral array. Okay, what we can also see right away, I'll share the screen again so we can look at it together, is that our iron is attached to chlorine, and chlorine is typically a weak field ligand, so it's also going to have a small delta value. All right, so we have to keep that in mind. Weak field ligand, small crystal splitting energy, small delta value. So now when we are going to set up our octahedral diagram, we have 5d electrons to distribute. We have a small delta value. That means that we're going to have a high spin complex. 1, 2, 3, 4, 5. Right, so what we end up with are 5 unpaired electrons. And obviously, because we have any unpaired electrons, that is another paramagnetic species. A species can be considered diamagnetic when it has 0 unpaired electrons. Okay, and let's look at 2 more examples of this. Oh, I did not want that. Oh well. Share screen. Okay, so we're going to look at 2 more examples. Unsurprisingly, they're giving us strong field ligands to consider now so that we can see how it's different. So we're going to start with CO, NH3, 5, NO2, 2 plus. Okay, so I want you to go through and first of all, figure out what the charge is on the cobalt here, because we're going to need to do that before we can distribute the electrons in our diagram. We know that the overall charge is +2. We know that the NH3 has a charge of 0, and we know that NO2 has a charge of -1. That means that the cobalt is going to have to be +3 for us to get a +2 charge back out. Okay. That means that we have to find the electron configuration for that. Where did we go here? Okay, so we're going back to the cobalt, which starts with 4s2, 3d, 1, 2, 3, 4, 5, 6, 7. We're removing 2 electrons there, 1 electron here. Okay, so we're 3d6 again. So we have 6 d electrons. All right. What we have here in terms of our ligands, we have NH3 and we have NO2. If we look back at our list, okay, which sharing it again now, NH3 is a strong field ligand. NO2 minus is a strong field ligand. Both of these have a large delta value. Okay, so we're going to end up with a very big difference between energy levels of the bottom level and top level. When we have a large delta value, this is going to favor your low spin complexes. So let's draw this out. Okay, so we have, sometimes when I'm drawing this out, I like to make it like dramatically different. So it's like that's your top level, and then like your bottom level will be like down here. So you can like really see the large delta value. Okay, we have 6 electrons here. So they're going to go 1, 2, 3, and then that 4th electron is going to look up there and go, nope. Let's go back to the beginning. 4, 5, 6. Okay, this is a case where we finally see a diamagnetic species here. We have 0 unpaired electrons. And our ion is diamagnetic. All right. So let's look at one more example. This one's going to be CO CN 6 4-. Okay. Right away, we should be able to look at the cyanide. Cyanide is a strong field ligand. You have to know all of your strong field ligands and weak field ligands by heart. You're not going to have that list on the exam. So take the time, if you just want to remember what the strong ligands are so that you can be confident that the other ones are weak, that's fine. But you have to be able to pick out the strong field ligands from the weak field ligands. Okay, so we know that cyanide is a strong field ligand. So again, we're going to have a large delta value, and it's going to favor a low spin orientation if it has the choice. You don't always have a choice with it. Sometimes there are too few electrons or too many electrons, and the electrons are forced into a certain orientation. Okay, but if it has a choice, it's going to choose a low spin complex. As far as the charge, we have a -6 total from the 6 cyanides, an overall charge of -4. That means our cobalt is going to be +2. So again, I'll rewrite this every time just so we're all on the same page. We're going to start out with 4s2 3d7, and we're going to remove these 2 electrons. So we're going to end up with seven d electrons. Okay, and if our 7d electrons are going to be trying to fill this strong field orientation with this very, again, large delta value here, your electrons are going to go 1, 2, 3. Electron number 4 is going to say, I'm staying down here, 4, 5, 6. And in this case, that 7th electron is going to be forced up top because there's nowhere for it to go. So when all of our electrons are distributed in this low spin complex, we end up with 1 unpaired electron, which gives us a paramagnetic species. It's still a low spin complex because it still has many electrons that are paired, but it does have some magnetism to it because it has that 1 unpaired electron up there. All right, those are the questions from your textbook. As always, if you have any questions, you can let one of us know and we can talk about it. Other than that, keep on studying.